The space-time diagram shows the Earth frame with the world line of a spaceship as moving away from Earth. Question 8. Determine the speed of the spaceship relative to Earth. To find the speed of the spaceship, it's the same as to find the speed of the moving reference frame. We use the next formula. The tangent of theta is equal to v over c, where v is the required speed, c is speed of light, and theta is angle between ct axis and ct primed axis. It's here, and also it's angle between x-axis and x primed axis. And choose any point on ct primed axis so that we get a right angle triangle, and tangent is what opposite of adjacent, and you can see that it's 3 kilometers, it's 5, so tangent is 3 over 5, 0.6, hence v is 0.6 c. The next, a flash of light sent by an Earth observer at ct is 2 kilometers is directed towards the spaceship. Question B. Estimate using the space-time diagram the time in seconds when the flash of light reaches the spaceship according to the Earth observer. So when ct is 2 kilometers, it's here, and notice that an observer on the Earth relative to the Earth's reference frame, it's always at the origin, and notice that a flash of light or a signal which travels with the speed of light, it's always represented as a line at 45 degrees. Why? Because the same formula, tangent is v over c, v is equal to c, so tangent is 1, theta is 45 degrees. So a flash of light is represented on the space-time diagram as a line at 45 degrees. So we need just draw a line at 45 degrees, and this point is an event when this flash of light reaches the spaceship, and we need relative to the Earth observer, so we need on ct axis this value. It's 5 kilometers, and it's value of ct, and it's called the time coordinate, and it is measured in kilometers, and we need in seconds, and then just 5 kilometers, which is 5 times 10 to the power of 3 meters, divided by speed of light, 3 times 10 to the power of 8, and we get that it's approximately 1.7 times 10 to negative 5 seconds. Another way how to find it, let's consider x-axis. It's in the Earth's reference frame, it's the origin, and a light signal is sent, but when it is sent, the spaceship is not at the origin. And where is it? It's this moment of time relative to ct primed, and in the Earth reference frame, directly from a graph, it's at a spaceship is at coordinates which is 1.2 kilometers, and let t be the required time, a light signal to reach the spaceship, but during this time t, a spaceship is also moving, and it travels some distance, which is what? Speed times time, so it's 0.6 c times t, and time it's what? Distance over speed, and it's time for light signal to reach the spaceship, and distance to be traveled is what? This is the 1.2 kilometers plus this additional 0.6 ct, and divided by c, speed of light. And you can see that we get ct is 1.2 plus 0.6 ct, so 1.4 ct is 1.2 kilometers, hence ct is 1.2 over 0.4, or the same as 12 over 4, it's 3 kilometers. But what does it mean? It's time required light signal to reach the space ship, but as coordinate, it's what? It was sent at coordinate 2 plus 3 required, so as coordinate it becomes 5. And we get the same result. The next, determine the time coordinate CT prime when the flash of light reaches the spaceship according to an observer at rest in the spaceship. So we need the same event but in CT primed coordinates. This event that this signal reaches the spaceship but in moving reference frame. And also there are two ways. The first is just how to find this coordinate if we know what coordinate on the same event on CT axis. And relation is the next. 1 unit, and it's always true, 1 unit on CT primed axis corresponds to, and you use horizontal line, not slant lines, corresponds to 1 times gamma, and gamma is gamma factor, it's 1 over square root 1 minus v squared over c squared, and for 0.6 c it's 1.25. So 1 on CT primed axis corresponds to 1.25 on CT axis, and notice that scales are not the same. If you use a ruler, 1 centimeter on CT, it's some value, it's not the same as 1 centimeter on CT primed axis. Scales are different. Or using again horizontal line, 1 on CT corresponds to 1 over gamma on CT primed. Hence, if we know that 5 on CT, it's 5 over gamma on CT primed axis. And the same for X. So it just becomes 5. So CT primed is 5 kilometers divided by gamma. And gamma is 1.25, so it's 4 kilometers. So it's 4. Another way is to use that space-time interval that S is invariant, and it's what CT or delta t squared minus x squared is equal to CT primed squared minus x primed squared, and it's x primed is what its coordinate. Its coordinate in moving reference frame relative to the spaceship, but an observer in moving reference frame is always at the origin, so it's 0. And it's required, and x and t are coordinates of what of this event, and you can see that CT is 5 and x is 3. CT in kilometers, CT is 5, 3. You can see that CT prime squared is 16, so CT primed is 4 measured in kilometers. And that's all for this question.